So one of the reasons why I like to go back to systems of equations is the algebra skills that are thrown into this section are skills that you guys are going to use throughout the whole entire school year. Solving for x, solving for y, substitutions, back and forth, visualizing common factors, visualizing the idea of scalar multiples, things like that. There's a lot going on within systems of equations that will help you throughout the entire school year. Now, last year, when I did this unit, I did it really kind of towards the end, and it was thrown in with a little bit of matrices and whatnot. I don't know if we're going to get into any matrices. If we have time at the end of the year, we'll do it. But for right now, I just want to kind of fly through systems today. We'll probably do some systems of inequalities tomorrow, which is graphing them, which is really quite simple. And then come Monday, we'll start with what's called linear programming. Linear programming is a little something that's kind of like word problems on crack-ish. Maybe crack-like. But it takes a while to get accustomed to the vocabulary of an algebra 2 word problem. And it's not as difficult as it sounds, it just takes a minute to understand how you set things up. So what I want to do here is look at systems of algebra, systems of equations, and see if you guys remember ways of solving systems of equations. So we just do this one at a time. What was one method to solve a system of equations? You guys remember? There's like 3 of them. Substitution. When do you think you would use substitution? Well, I see 4 of them, so I found them. All right. Obviously, what I would do here is I would use substitution if a variable is by itself or can be easily. What I'm talking about here with substitution is basically putting one in for another. It eliminates one of the variables for us. Now, in the example I have here, I have 3x plus 4y is negative 4. Second equation is x plus 2y is 2. Substitution would work for this one rather simply, because I can get that second equation, I can get x by itself. How? Yeah, good. Just subtract the 2x. So I know that x has to equal 2 minus 2y. You okay with that?
Yeah.
What would I do with that x then? Okay, substitute it up at top. So you have an x already isolated, then you just substitute back up here. And then you have one equation with one variable. You wind up with 3 times the quantity, 2 minus 2y, plus 4y is negative 4. I don't know if I discussed this with you guys yesterday or it was 12th hour, but a lot of times when you get going with these problems in the book, there's so many problems, so many numbers and letters, something they're all kind of compact together within the problems. It's very easy to accidentally write one part of one problem with another part of another problem. So if it starts working out where everything looks awful, just double check you wrote the problems down correctly. Okay, I'll show you when I put up some of the homework stuff here. What do I do now? Distribute. So we have 6 minus 6y, 4y, negative 4. Bring the 4 over, move the 2 the other way, and you get 5 for y. Which means, to solve for x, all I have to do is put 5 back in for y. And I would do that here because I already have isolated x. So 2 minus 10 is -8, good. Now the only other thing with systems of equations, if you remember I kind of skipped this section. When you first did systems of equations back in Algebra 1, you guys probably graphed them, right? And you figure out where they ran into each other on the grid. So you were finding an ordered pair. When you do it this way, you're still finding the ordered pair, but you were just using algebra. So your answer would just be -8 and 5. That's how I would write it. Does that make sense?
Yeah.
Graphing systems of equations to solve for the intersection is so unbelievably inefficient. It's so much easier to use algebra. Okay? So much easier. You guys vaguely remember this?
Yeah.
One of the other things that we can do, that's right, did that one.
Now what can you do?
So we have substitution. The other methods are kind of the same. So let's see, substitution. If variable by itself. Do I have to write or easily? I mean, you guys get that part, right? The variable can be by itself. You had elimination. You could add them together, or you could subtract them. And what happens there, I don't have your brother in class. In board space. You could add the equations together to eliminate a variable. You could subtract the equations together to eliminate a variable. And then the other one is we call linear combination. Which basically is get same, bless you. Get the same coefficient somewhere. Now, when I'm looking at linear combinations, that's kind of usually what you wind up doing. Not everything always winds up where you get 2x minus 4y is 13, 2x minus 5y is 8, where you can just subtract them together, the x's go away. It's not always going to be that clean. What you're going to want to be able to do is create having the same coefficients with either the same signs or with opposite signs. And that way we tell whether or not you're going to add them together or subtract them. So if I'm looking at this equation here, does everybody agree that I can take the top equation and multiply it by 2, and I get 4x, which would be the same as the 4x below it?
Yeah.
You guys remember doing that?
Yeah.
Okay. So what I would do is I'd take this top equation and multiply everything by a factor of 2. It's called a scalar multiplier. Since I've written down the bottom equation, go
Wait,
ahead.
is this, what example is this?
This is a linear combination
Okay,
style.
thank you.
Yeah. By multiplying across everything here, I'm just going to rewrite it right below it. So I get 4x minus 8y is 26. By going into that linear combination first, now I have a scenario where I have same coefficients, same signs, or same coefficients with opposite signs. In this case, does everybody see how I have the same coefficient with the same sign for the 4x's?
Yeah.
How would you eliminate those two? Good. So here's the two little rules here for adding and subtracting. If you have the same coefficient with the same sign, you subtract. If you're adding, you have the same coefficient with opposite signs. Is when you add. It becomes very evident if you have forgotten this from a couple of years ago. Once we do a couple examples, you're like, oh yeah, I remember this. Like I said, this section here is just a lot of practice of quick multiplying, recognizing greatest common factors, what kind of things you can do to eliminate values. I kind of oversimplify these things when I do this. I split it up because there's 3 parts I have to subtract, so I just make sure I put in 3 subtraction parts, just so I don't miss anything. And then I take a quick second and write it. 4x minus 4x, negative 5y minus negative 8y, and 8 minus 26.
We have to rate it like that.
You don't have to. It's a suggestion that I always that I do, because it forces you to make sure that you don't mess with those signs, because there's so many negatives that can get thrown in here. I know how you guys will mess that up. Yes, sir.
For the same coefficient sign thing, does that apply to the x's or does that also apply to the y's?
Either one of them. Either one of them. It could be. Sometimes it might be easier to eliminate y's. Sometimes it's easier to eliminate x's. My opinion, I'm going to try and add them together more often than I will subtract, because I'm less likely to miss a sign value, because subtracting a negative. I know that's what you guys screw up. That's all. 4x's go away. That becomes 3y. And what is that? Negative 18. Y, therefore, is negative 6. Then all you have to do is substitute that back in to solve for x. Will it matter which equation you use? No, not at all. Has no difference, makes no difference. So I'll just use the second one this time. So you have 4x minus 5 times negative 6 is 8 plus 30. And subtract 30, what do we get? Negative 22. Negative 11 over 2. And I will say that you will see a lot of fractions in decimal.
Does it matter which one you use? No.
What's that?
I just asked, does it matter which one you use?
No, not at all. If we did it right, you should get the same answer. Okay? Don't freak out. You're going to see a lot more fractions when you do these things. You're probably doing it right. It's just what happens in algebra 2. Okay? We vaguely remember that?
Wait, what is x equals 11 over 2?
Negative.
A negative.
Yeah. I just did it in my head because it's 22 over 4, so I just cut it in half to write it and simplify it out. Do you guys know how to simplify fractions in here? Let me show you. Real fast. I still got to get the emulator software here. If I take negative 22 divided by 4, I get negative 5.5. If I hit math, enter, enter, it creates the fraction. Or if I start with a fraction bar in my calculator by hitting second y,
Alpha y.
Thank you, alpha y equals. If I start by hitting alpha y equals and then enter, it automatically creates a fraction bar. If I type in negative 22 over 4, it'll automatically simplify that out for you. Okay? Okay.
But, like, are you ever going to tell us you have to use like one of those methods, or is it
Nope.
just be like solid?
I honestly, the book says use this method, use this method. I don't care what method you use.
You can use anything.
Yeah, absolutely. I wouldn't use substitution for something like this because you get some pretty gnarly looking fractions, but I'm not going to say one way is better than another at all. I will never say you must use substitution, but yet elimination might be quicker.
Okay.
Why do you look so worried? Oh no, she was looking. I mean, it's okay. Here, air 5. Yeah. You know somebody missed an air 5 once? I'm not lying. No, go like this. Air 5, ready? She missed an air 5. I'm not lying. A kid missed an air 5 last year, and I was heartbroken. How do you miss an air 5? You can't.
Well, apparently you can.
Apparently. Okay?
She didn't even know what she didn't know pizza. No.
Choose method. Choose your own adventure. There's multiple ways to do this. You remember those books?
Yeah.
Those are always cool.
Sorry.
I'm looking forward to. Yeah. All right, so I actually heard someone use a method that I would have done, which I think is quicker because. Well, I'll show you. Look at the second equation. What can you do to all three of those? Now if you didn't do this, it's okay. If I take the 5's out, I get negative x plus y is 3, which means y is x plus 3. What most of you guys did, probably was multiply the top by 5 and the bottom by 2. You know what? There's nothing wrong with that. The only reason why I would have done that is because I recognized right away that there's a GCF that leads to substitution really quickly, really fast. Rather quickly. Alright? It doesn't matter what you use. I would do it this way because I'll be done pretty quick. Since most of you guys did it this way, I will walk through it that way for you. So you had 10x, 15y is negative 5. One suggestion also, when you start multiplying these things together, since you're going to have to subtract all of it, space it out a little bit. Give yourself a little bit of space. So you have negative 10x, 10y is 30. So now when I space it out, I've got more room to write. Everybody see that?
It's the same thing.
These go away. This is 25, and that's 25. Y is 1. And then you substitute back in. So I have 2x plus 3 times 1 is negative 1. Add the 3, all of a sudden we get x is also
All of a sudden.
1. Right? No.
No.
Wait.
You're wrong.
Oh, I did subtract. Yes, negative 2. Sorry. I was adding. I'm sorry. 2x, negative 4. There we go. Math is hard, yes.
I did like a different thing and I got it.
Thank you. Such support system we have. Everybody's pulled for everyone. Okay.
Those ones I forgot about. Those are gone. Bye.
Not so bad? Last one, I'll give you some problems.
It's kind of like the perspective of like how like the
I don't want to do it. I'm bored doing math. Somebody go do it.
I times it. I just did times 3 and then times 2 and then I got 3 y's and negative.
You're both not wrong.
Well, you can do that.
Here's what I would do. Just because you can't do it pretty easy.
You
See how these guys are opposite sides? What am I multiplying 2 by?
It's probably
Just leave the sign. Just multiply by 4. Because then I can add them together and I don't have to worry about the sign. So if I multiply the bottom equation by 4, I know it's a little bit messy. It's a long way, but it's, in my mind, I'm seeing it's a nice, easy way to eliminate the loss. So I have 2x, 8y, minus 8y, and then see it's 32, negative 16. If I add these together, these guys go away. 2 and 12 is 14. 8 and negative 64 is negative 56. If I divide these out, I believe you get negative.
Oh, so then you have to
There's many different ways to do it.
So what if I did divide that top one right then?
If you did that, then you had x plus 4y is 4. Then x is 4 minus 4y.
Oh, and then you just put it.
Right. So there's many ways of doing it. As soon as I see that I have opposite signs, my eyes are always drawn to that because I know I can add them together and I can eliminate them. So I try to eliminate those two. Whether or not I can do substitution or anything else, I always thought that that's a cleaner way to do it. That's just my own opinion.
If that makes more sense, if you point that out, then I know what to look for, I know what to do. Because otherwise I was like gonna try to do these two, you know.
And you can. You have to subtract it.
But I got really confusing, so.
It can be real quick. If we read the chicken scratch,
Thank you. I don't think I did that.
we got -4 and 2.
There you go.
So he used the substitution method on that one, brought it through. 14. Yeah, it works. There's many ways of doing it. I was just talking with Abby and Alicia here. One of the things that my eyes are drawn to whenever I do work with systems of equations, the moment I notice that I have opposite signs, right there at the y's, I try to eliminate those right away. Whether or not I go and do what you did by dividing out by the multiplier and substituting in, I noticed that I can eliminate the y values just by multiplying that bottom equation by 4. And add them together and it works the same way. The numbers might be a little bit larger, doesn't matter, I got a calculator, it's not that big of a deal. It's just, if you draw yourself thinking about using adding or subtracting, adding is always easier because you don't have to worry about your signs. One last little question here when we talk about ways that lines intersect, because I did not bring this up. Bless you.
Thank you.
There's 3 things that can happen with 2 lines. Do you remember what those 3 things are? I'm sorry. There's 3 things that can happen in space with 2 lines. They can intersect. 2 lines, excuse me. 2 lines can intersect and have 1 point in common. 2 lines can be parallel. We're in the same plane. How's that? 2 lines can be parallel. If they're parallel, do they have anything in common? No. They have that, but they have no points in common. There's no points.
Or they can be the same, like, line.
Or they can be the same line, and then what happens?
They're all,
We have infinite, well, sorry, that's crooked. You can have infinite solutions. Bless you.
Is that important?
To me, that just looks like 2 fishes connected.
Why does your mind go to that?
It's fish.
No, it's not.
That's how we explain fish. See? Look. That looks like 2 fishes.
It's a hyperbolic paraboloid.
What? Exactly. Why didn't you just say that?
Did I tell you about hyperbolic paraboloids yet?
No.
No.
Seriously?
Wait,
What else does that look like?
that looks messed up.
Like a
Looks like an
like a Pringle.
A Pringle. The guy that came up with the guy that came up with Pringles was very upset about potato chips. Potato chips tend to crack and break as they get to the back, as they get to the bottom of the bag. So, what he was a mathematician. He thought of a way that, well, if I make, you guys know curves and arches are one of the strongest structures you can make.
Yeah.
Well, if you curve through on the chip stuff, you can stack them. Therefore, granted they still can break, they tend to hold their shape better. So if they stack them, put them in a can, he thought about, well, what's the best way to stack them? Well, if they're flat, they're all going to break. You put a curve to it, therefore they hold their rigidity as they go through. So it is a hyperbolic paraboloid made by Mr. Pringle, who was some math nerd who was hungry.
Worth it.
Wait.
Science. I don't know the science, but okay. So, like I said, within systems of equations, you can have one solution, no solution. If it's no solution, that means they're parallel. Or if they have infinite many solutions, which means that they are the same line. Algebraically, here's what happens. You get x equals some number, y equals some number. You know the ordered pairs work. No solution, you wind up with something like this. 7 equaling 3. That doesn't work. You get a false statement. If that happens, double check, just make sure you didn't screw up, because you never would screw up. And then if you have infinite solutions, that means you have the same equation, which means you wind up with what's called a true statement. You might get 4 equals 4, or x equals x. If something like that happens, when you wind up with a true statement, you wind up with an infinite many solution. Okay? You might remember that from way back in the day. You might not. Just a little precursor of stuff that does show up. So a couple of problems for you guys to do. This is section 3.2. The tab is up on the website already. Oh, I forgot my book. It is on page 153.
I'm still mad about this.
I would like you to do numbers 35 through 40 and 45.
Yeah.
Okay? I'd like you to do those, please.
You don't need them. Get out of here.
Is that your group for
Okay?
Yeah.
It was Harmon, Sydney, Beck, teaching flying, and then Warren, Beckett, and Warren, Boosting.